All right, let's talk about one of the most fundamental little gadgets in all of electronics. It's in your phone, it's in your car, it's in, well, pretty much everything. It's a tiny device that literally holds pure energy. We're talking about the capacitor.
So let's start with a really basic question. A huge engineering challenge, actually. If you wanted to build something, a container, just to hold raw electrical charge, how would you even begin to do that? Believe it or not, the answer to that question is what makes our whole digital world possible. You know, the core idea here has a name, capacitance. It's literally the capacity an object has for storing charge. We measure it in a unit called the farad. And for any engineer, this is the name of the game. How do you cram the most capacitance into the tiniest possible space? Okay, let's really get into it. To understand the absolutely brilliant solution that engineers eventually came up with, you first have to appreciate just how big the problem was. So let's start with the simplest, most basic design you could ever think of. Just a single, lonely metal sphere floating in space.
Now, the physics behind this is pretty straightforward. An object's capacitance, that's C, is directly proportional to its radius, r. All that other stuff, the 4 pi epsilon naught, that's just a constant. Don't worry about it. So the formula tells us a really simple story. You want more capacitance? Just build a bigger sphere. Sounds easy, right?
Well, this is the exact moment where a neat little idea from a textbook slams face first into the wall of reality. Let's see what happens when we try to build one of these things with a useful amount of capacitance. Let's actually run the numbers. We're not asking for much. We're just aiming for one single farad of capacitance. That's a pretty standard unit. So how big of a metal ball are we going to need? The answer is 9 billion meters. And no, that's not the diameter. That's the radius of the sphere. It's a number that's so ridiculously huge, it's hard to even wrap your head around it. So let's try to put that into perspective. And this is where it just gets absurd. Our little 1 farad capacitor would need a radius almost 1,400 times bigger than the radius of planet Earth. It isn't just large, it's astronomically mind-bogglingly huge. You're not exactly going to slip that into your back pocket.
So yeah, the conclusion here is pretty obvious. This design, as simple as it looks on paper, is a total, complete non-starter for any kind of real-world use. We need a much, much smarter way to do this.
Okay, so if a single planet-sized sphere is out, what's plan B? Well, this brings us to the breakthrough design that you will find inside pretty much every piece of electronics you own, the parallel plate capacitor. And the structure is incredibly simple. Just picture it. You take 2 metal plates, you give them some surface area, we'll call that A, and you stick them right across from each other, separated by a super tiny distance, D. When you hook it up, positive charge piles onto one plate, and an equal amount of negative charge goes to the other. This tiny change in the setup completely rewrites the rules for storing energy. Here's where the magic really kicks in. Those separated charges create this nice, uniform electric field in that little gap. That field creates a voltage between the plates. And by connecting the dots between the charge, the voltage, and the actual shape of the thing, we can cook up a brand new and way more useful formula for capacitance. And there it is. That's the master equation. The capacitance C equals that constant epsilon naught times the area A, all divided by the tiny distance D. This little formula is basically an engineer's cheat sheet. It shows us the 3 knobs we can turn to get more and more capacitance. So let's put on our engineering hats for a minute. Imagine your boss walks up and says, "Hey, I need you to design a capacitor with the absolute highest capacitance you can get, but it's gotta fit in this tiny little box." What do you do? Well, lucky for us, the formula gives us a roadmap. We've got 3 options. We can make the area, A, bigger. We can make the distance, D, smaller. Or we can mess with that little constant thingy at the front, the epsilon naught. Let's think through the pros and cons. All right, option 1, increase the area. Sure, that works, but it makes the capacitor physically huge, and that kind of defeats the whole purpose. Okay, option 2, decrease the distance. Now this is a big one. It boosts capacitance fast, but you can only push the plates so close together before they touch and zap. Short circuit, game over. So that leaves one option as the clear winner. The smartest, most elegant solution is to change what's in the gap. If you swap out the air or vacuum between the plates and instead stick in a special insulating material, we call it a dielectric, you can boost the capacitance like crazy without making the device even a millimeter bigger.
This is the secret sauce. It's the reason two capacitors that look identical can have completely different values.
Okay, so we figured out how to make a compact capacitor. But why do we care so much? Why this obsession with cramming more and more capacitance into a tiny space? Well, it's because the end goal isn't just about storing charge, it's about storing usable energy. And this brings us to what's probably the most important concept in all of modern electronics: energy density. The real challenge isn't just how much energy you can store in total, it's how much of that energy you can pack into a microscopic volume. That's the whole ballgame.
And what's really beautiful is how simple the physics is. The energy density, all that energy we've packed in there, it only depends on two things: how strong the electric field E is, and the properties of that special material we stuck in the gap. That's it. So let's just recap the journey here. We started with a simple metal ball that turned out to be impossibly huge. The fix was a much smarter design, the parallel plate. Then we made it even better by putting a special material inside. And this whole evolution was driven by just one single-minded goal: to cram the most energy into the smallest space imaginable. And honestly, this principle is what's behind almost every piece of tech we have. Think about the battery in your phone or the power systems in an electric vehicle. The mission is always the same. How do we pack more power into a package that's smaller, lighter, and more efficient?
And so I want to leave you with this final thought. If the material is the real key to unlocking more energy storage, then the next giant leap in technology, I'm talking revolutionary batteries, crazy fast computers. It's not just going to be a clever bit of code. It's probably sitting in a material science lab somewhere, right now, just waiting to be discovered.